Let's try to apply some higher level thinking using the concept of general acid catalyzed mechanism to solve the problem that's shown here. We're asked to come up with a way to, in one step, produce this structure from 3 reactant molecules, and we're asked to draw the transition state and provide the curved arrow notation that would get us there. And so if we think about what's going on, we have the addition of a molecule of methanol, that's this bond right here, into the carbonyl carbon. As that bond is being formed, the pi bond is breaking, but the pi bond isn't generating an oxyanion. Instead, that pi bond pair of electrons is being used to pick up a proton on what was the carbonyl oxygen. It's picking that up from our general acid, a protonated form of methanol, and that bond is breaking. And so from that set of arrows, we can draw a transition state structure that's going to show the carbonyl carbon being attacked by an oxygen from the methanol. That oxygen carbon single bond is being made in the transition state. That methanol molecule is acquiring a positive charge. You can see that in the final product, that positive charge resides on that molecule. The carbonyl oxygen to carbon double bond is being broken, so we need to say that we need to show that as a dashed line, and then we need to show that there's the formation of an oxygen to hydrogen bond, and as that bond is being formed, the hydrogen to oxygen bond from the molecule of methanol is being broken. So there we have that molecule that was protonated and donating its proton. Its diminishing charge should be reflected with a partial plus. That represents the transition state structure, and you can see in the transition state structure there's a lot of bond making and bond breaking, and 3 entities come together. In the second half of this problem, we're asked to deal with the case where this had been a specific acid catalyzed mechanism, and we're going to consider the intermediate that would have been formed. Since we're dealing with a ketone, we know that it's going to be a protonated form of that carbonyl that would serve as the intermediate that would lead to the addition of that second molecule of methanol. So we need the protonated form of that, and there it is, positively charged carbonyl of that molecule of acetone. Then we're asked to compare the change in pKa. And the change in pKa means, in the case of the general acid catalyzed reaction, we go from a protonated molecule of methanol, actually it looks a lot like hydronium ion, H3O+, to what looks very similar, a protonated form of what looks like a molecule that is an ether. And so we would expect, because both of these resemble H3O+ hydronium ion, that there really is almost no change in pKa. But if we look at what goes on in the next case, we have the protonated form of a ketone that has a pKa for the product of -7, and then we're going to take the difference of that with the acid that had donated that proton, the protonated form of methanol that has a pKa of about -3, and so the net change is a delta pKa of -4. In other words, we took something that was a weak base, the carbonyl oxygen, and was protonated by this proton coming from the proton that was not as strong of an acid as the acid that we generated. The acid that we used to protonate the carbonyl wasn't as strong as the acid that we generated. So, in other words, we see that for this specific case, it was actually a very uphill free energy climb in order to make that pKa change from a weaker acid to a stronger acid. The last question we're asked to answer is, what is the more ordered of the transition states leading to the intermediate that we generated in the case of the specific acid catalyzed mechanism? In there, 2 things came together and formed this intermediate, or the case of the general acid catalyzed mechanism, where 3 things came together. 3 things came together all at once in the general acid catalyzed case, that must be the more ordered of the two. So we have 3 species involved in the transition state. And so, there's an important lesson to be learned there. Anytime we have a general acid catalyzed mechanism, it's almost certainly going to involve multiple species simultaneously coming together. This is perfect for an enzyme which is able to order its reactants in just the right way and bring multiple reactants together. It's less likely in the case of, say, a reaction happening in a flask where bringing all of the components together at the right place and at exactly the right time is somewhat more difficult. And so the general acid catalyzed mechanism is going to serve us well when we start to talk about enzyme catalyzed reactions.